3.1. Using figure 10, give the 6-figure grid reference for a shingle beach. Shingle is just big rocks, pebbles, not sand. Shade one of those circles in. So the correct answer here is C, because here is your figure. You can see it's at the coastline. You've got a few beaches that you can see. Now, interestingly, there is no key, so you just really have to work it out. These are the sandy beaches, and if you look right down the bottom here, you can see another beach, but it's got those black dots on, which represent shingle. So the correct answer would be 59.6, about halfway, 59.6, 10.6. So it points to this bit here. So that's the shingle beach. Answer is C. 3.2, using figure 10, which of the following statements best describes the features of grid square 6016? So again, we'll go back up to the map. 60, 16, oops, is right at the top. So it's this square here, if I can zoom in a little bit. So what best describes this square? And the answer is D. A beach with groins, that's what these black lines that stick out represent, those wooden groins. A small coastal settlement and an A road, which is this purple one here. 3.3. Using figure 10 again, how long is the coastline between X and Y? In one of those circles only. So I'll have a look again. X and Y. So get your ruler out. You need to measure how many centimeters it is. Now, unlike a lot of maps, there is no scale bar down the bottom. So how do you know what the distance is between these 2 points? Well, if there's no scale, it will give you a bit of a ratio at the top here. So in this case, it's 1 to 50,000. This means that every 1 centimetre on the map, in reality, is 50,000 centimetres. Now, you need to realise that in 1 kilometre, there is 100,000 centimetres. So in other words, every kilometre, every 100,000 is going to be 2 centimetres. So you'll work out the distance and then you'll realise that the answer is D. Works out as 3.4 kilometres. Study figure 11, a photograph of part of the coastline shown in figure 10. Using figures 10 and 11, in which direction was the photographer facing when this picture was taken? We've got 4 options. So we've got the spit, and we've also got the estuary and a bridge. So let's see if we can see those on figure 10. Okay, so this might take a little while to find, but think about what we've got. You've got the spit, which is there. You've got the estuary here, and then you've got in the foreground the bridge going across. So the photographer would have had to been standing somewhere here to then take a photograph of the bridge, and then the water, and then the spit, which must be Z here. So which way are they facing? South is down, west is across, so it's diagonal. So the answer will be southwest. 3.5, using figures 10 and 11, suggest one reason why the area in grid squares 6014 and 6015 show evidence of material being dropped or deposition. So why is beach material like sand being dropped in 6015, 16, 16? Well, what we could say is, first of all, we realise there's a river here and then the sea here. So you can imagine the river flowing out to sea and here. As it reaches the sea, though, obviously its energy is going to slow down because the sea is probably going to be moving in a different direction. And as they meet, they're going to hit each other and it's going to slow the water down. So when water slows down, that is when it drops its material. So that's why there's probably a lot of sand here and here. You could also potentially mention the process of longshore drift. So it could be moving in a zigzag motion from the north here, going all the way along, but the coastline changes direction here because you've got this bit, and then obviously you've got the river in the way, and then the other shape here. So you could say, you know, as longshore drift happens, the coast has changed shape, which has slowed the process down and dropped a lot of material here. Feature Z labelled on figure 11 is a spit. So for 4 marks, we need to explain how spits form. So we could start by saying the formation of the spit usually begins due to a change in the direction of the coastline, if the coastline ends. One source of material building up the spit is from the key phrase longshore drift, which brings material from further down the coastline. Material is carried along the shore in a zigzag fashion by the waves as they swash material up the beach at an angle which is the same as the angle of the wind, and the backwash material back down the beach at a right angle, which is determined by gravity. We could also say, if we have a quick look back here, click at the map where this spit is here. Here we are. So we can say that there's longshore drift that's happened. We can also say that there might be some sediment that might have been out onto the seabed here, or indeed in the river, and as the two bodies of water meet, they will slow down, and then they will drop loads of their material to make the spit bigger. You could finally say that as wind changes its direction, potentially that is where the spit starts to change its shape. As we've seen, this one curves round a bit. So the prevailing wind has changed direction, which gives it a hook. 3.7. Hard engineering strategies are effective in protecting the coastline. Do you agree with this statement? So, 6 marker, you've got your short statement there, but you've got to assess whether you agree with it or not. So we're looking for a bit of a balanced answer to access the level 3 grades, which is 5 or 6 out of 6. So in terms of hard engineering, you've got things like coastal groins, sea walls, riprap, also known as rock armour, and many others as well. But ideally, you sort of maybe suggest what hard engineering is first, which is sort of man-made artificial ways to protect the coastline. Now, are they effective? Well, I would be saying, first of all, yes. You know, something like a seawall is a big, sturdy barrier between the sea one side and the coast the other. So the idea is that the seawall absorbs the wave energy, but it can be curved as well, which is a bit more expensive, but it doesn't just absorb the wave energy, it reflects the wave energy back into the sea to slow the waves down, to reduce erosion. Something like groins, you could say, well, they are fantastic because they stop material, they trap material from being transported further down the beach due to the process of longshore drift. And why is that good? Well, a bigger beach acts as a natural barrier between the sea one side and people's homes or the cliffs the other, which is great. But also it makes the beach bigger, which will encourage tourism. And the money through tourism can also be used in investing in other hard management strategies. Finally, riprap or rock armour, these are big, hard rocks. And the idea being that they're put on the beach so the waves hit them and they absorb the energy rather than maybe the softer cliffs behind. So all of those things, you explain what they are, there's some good advantages to them. But is it all good? Is it all effective? Yes, but you could say, well, actually, these things are incredibly expensive. A seawall, we're talking thousands and thousands of pounds every metre. Some of the things like groins, they might restrict access to the beach, or groins again, a lot of them are made out of wood, which, although will last a long time, will also rot after a few decades. Things like gabions as well, they're the wire cages with the rocks in the middle of them. In stormy conditions, or if you've got lots of destructive waves, they can be damaged and pulled away from the back of the beach, or the cages can be open, which could cause harm to people or the wildlife. So I would be balancing my answer saying, well, yes, they are effective, explaining why, but also why there might be some negatives with them as well. 4.1, give the six-figure grid reference of the mouth of the river Cuckmere. So the mouth of the river, that is where the river meets the sea. So you've got four options. I'll zoom into the figure. Here it is. So you've got the river coming down here, and then you've got the sea here. So the answer for the first question is B. 51.6, so just over half, 51.6, 97.7. There is where the mouth of the river is, as the river meets the sea. Next question, 4.2. Using figure 12, which grid square matches the following description? There is a meandering river. Land is flat in the south, but it rises to 70 metres in the northwest. Two secondary roads pass through the area. So if we have a look up, the answer is C, which is 51.01, which is the bottom left-hand corner for this square here. So you can see the meandering rivers as it snakes around. You can see one of the secondary roads there, one of the secondary roads there as well. So 51.01. Figure 13, this is a photograph of the same river and its valley. The question, using figures 12 and 13, can you give the grid reference of point X on figure 13? So if we have a look again, so this is figure X here. Looks like there's a man-made channel that has cut across the old path of the river, and here is the mouth of the river as it meets the sea. So if we have a look on the map, so the answer, remember we have to do a six-figure one, is 51.7. Again, it's about there. 9.85. So it'll be around about this point here, because you can see the old course, you can see the new channel there. The answer, 51.7.985. 4.4. Using figure 13, describe one feature of the river Cuckmere where it reaches the sea at point Y. So what can we see at Y? Well, just a reminder, this is the river, and here is the sea. So any features here? First of all, you don't get any credit to reference to any human features, like we've got a few groins, we've got a few houses, etc. So what we need to say is we can see there's lots of deposition. So the river has dropped a lot of material. That would be worthy of the mark. You could say that the river is cutting through the beach material. Or you could say the river becomes narrower and straighter just before it reaches the sea, certainly compared to the river out here. 4.5. Using figures 12 and 13, suggest why there is a straightened channel next to the river meander. So if just go back to the figures, there's your natural meander, and then you've got the more straightened channel here. So why is that? Well, any of these answers will be fine. It's all linked to the idea that if a river, is straighter, it's going to carry water away from an area a lot quicker. And that's going to be great, because if you take water away quicker, then it's going to reduce the flooding risk, because water isn't going to stay, it's just going to flow as quick as possible to the sea. You could also have the fact, if you realise there's farmlands around it, that maybe water has been transferred to this area to help with irrigating the crops or the fields. And although it's not mentioned on the mark scheme, maybe an idea of transporting goods perhaps out to the sea. So any of those answers should get you the mark for that question. 4.6, feature Z labelled on figure 13 is a floodplain. For 4 marks, we need to explain how floodplains are formed. So we could start by saying what they are. So floodplains are large, flat expanses of land that form on either side of the river. So if we have a look at the diagram, this is basically your floodplain area. So either side of the river, when it floods, it's going to be underwater. So what happens then is the river in sort of the middle and lower course, it's going to be carrying a lot of quite fine material at this stage. And the key terms for this material is either called alluvium or silt. And you can say that as the water floods, all the suspended material gets deposited, drops either side. Now the bigger material won't go as far. So as we can see here, you've got a cross section of the river before the flood. When it floods, you've got the bigger material that's just going to go onto the banks of the river, and then the very fine material is going to be spread out and go a further distance. So these things here, these mounds that are just on the sides of the floodplain area, these are called levees. Now, as the water recedes and goes back into the river, these levees remain, and then you've got the floodplain area this side and this time. So every time it floods, the floodplain gets a little bit higher. And hopefully you can see from this diagram here, your river, you've got your natural levees, and then it's full of silt and alluvium either side that will build up over time. 4.7, the causes of river flooding are usually a result of human factors. So we're going to have to assess whether we agree with this statement or not. So in terms of human factors that can create flooding, loads of different things. So for instance, there can be lots of man-made surfaces such as concrete and tarmac, which are called impermeable. They don't let water through them. Therefore, water stays on the surface, and that is how it travels really fast because there is a lot of surface runoff. You could say in urban areas, towns and cities, you've got sloping roofs, you've got guttering, you've got a drainage system. Therefore, when it rains, water is going to get into the rivers very, very quickly. Therefore, potentially it could flood. Deforestation, you can cut down trees, that could increase the flood risk because trees intercept the water from going into the rivers. They're collected on the branches and on the leaves, etc. So cutting the trees down is going to be bad, particularly if we then turn it into a field, because farmers can plough fields. If you can imagine sort of rows of soil with all of their sort of gullies running through, that can also funnel water through the gullies from the fields into the rivers really, really quickly. Think of Boscastle as well. We had bridges there, which again acted as dams when things like trees collected under the bridges. So there's lots and lots of human impacts, but there are some non-human factors that we have to explain as well. So for instance, it could be to do with snow melt. If snow starts to melt, then there's a good chance of flooding. There might be a lot of rainfall. Again, nothing that humans can control, but can cause a river to flood. It could be to do with the soil might be already full of water due to a previous storm. So it could be what's called saturated. The soil type or rock might be very hard, which again is called an impermeable surface because the water won't infiltrate into the ground. So there's loads of different reasons. Final one, if there's a lot of rivers already in the area, we call that a high drainage density. So if there's lots of rivers, then the chances of flooding will be high just because there's lots of water in a small location. So you need to balance your answer, maybe talk a bit about Boscastle as well to sort of evidence some of your points and come to a balanced conclusion.